The current electric vehicle market relies heavily on a single battery chemistry. Lithium iron phosphate, or LFP, dominates commercial deployments because it offers a highly stable thermal profile and is easy to manufacture at an industrial scale. This chart breaks down the exact distribution of that dominance. In the Chinese market, CATL controls 38.9% with 19.53 gigawatt-hours installed, while BYD holds 20.9% with 10.49 gigawatt-hours. According to the Fraunhofer Institute's 2035 Plus roadmap, standard LFP chemistry sits at an energy density of roughly 200 watt-hours per kilogram. The industry's target for next-generation storage requires pushing far beyond this physical limit. To displace LFP in commercial applications, solid-state batteries must clear the 450 watt-hour per kilogram threshold, while maintaining the exact same strict safety profiles as their predecessors. Reaching 500 watt-hours per kilogram is a multidisciplinary engineering challenge. It requires solving for extreme charging stability at the electrode interface, while simultaneously ensuring the cell can be recycled economically at a global scale. The Fraunhofer ISI taxonomy classifies solid-state architectures by the material used to replace traditional liquid electrolytes. Removing flammable liquid solvents from the equation leaves engineers with three distinct solid electrolyte pathways. The first structural pathway is the Li-ox, or oxide architecture. Oxide solid electrolytes offer high mechanical and chemical stability. However, they are brittle and require high-temperature sintering during manufacturing, which complicates production. The second pathway is the sulfide architecture, or Li-Su. These materials are mechanically softer, highly malleable, and do not require sintering. Their primary vulnerability is severe chemical incompatibility with high-voltage cathodes and lithium metal. The third pathway is the Li-Pol, or polymer architecture. Polymers are the most established materials in terms of production technology, but they have historically suffered from low room temperature ionic conductivity, resulting in a low limiting current density. Generating 500 watt-hours per kilogram in a controlled lab environment is achievable across these methods. The central engineering bottleneck is architecting a cell that balances ultra-fast 20C charging with a chemical structure that allows for thermodynamic recovery at the end of its life. Researchers at the Chinese Academy of Sciences recently focused on the Li-Poly architecture. They engineered a high-energy solid-state battery utilizing a polymer network based on polyvinylidene fluoride, known as PVDF. The historical point of failure for PVDF electrolytes lies in the conventional plasticizers used to prepare them. These plasticizers exhibit poor electrochemical stability, resulting in continuous parasitic decomposition right at the electrode interface. The research team resolved this by developing a precise chemical strategy termed compatibilizing solvent plasticization. The process introduces a volatile compatibilizing solvent into the electrolyte preparation, temporarily improving the interaction between the polymer and the stable plasticizers. As the solvent evaporates during film formation, the plasticizer is physically locked inside the PVDF polymer network. This controlled evaporation creates a highly stable, lithium fluoride-rich interfacial layer. That boundary layer drastically reduces side reactions at both the cathode and the lithium metal anode. This chart tracks the empirical result of that interface. Operating an ampere-hour level pouch cell with a thin lithium metal anode and a tight negative to positive ratio of 1.1, the battery maintained 81.9% capacity retention across 700 cycles. This stability was achieved at a 20C charging rate, equivalent to a roughly 3-minute charge and discharge cycle. By surviving that extreme lithium flux, the pouch cell successfully outputs an energy density of 451.5 watt-hours per kilogram. Hitting 451.5 watt-hours per kilogram solves the performance challenge. But if a battery requires extreme thermal or chemical destruction to recycle at the end of its life, it is a commercial dead end. Current industry-standard recycling methods, such as pyrometallurgy and hydrometallurgy, are thermodynamically inefficient for solid-state recovery. They use immense heat and heavy acid to tear engineered materials all the way down to their raw elemental states. To address this macroscopic life cycle challenge, a research model from UC San Diego outlines a direct recycling architecture. They focused on recovering the highly promising sulfide solid electrolyte, known as Li6PS5Cl. This diagram illustrates the proposed direct recycling flow. Safe battery disassembly moves the cell stack directly into a solution process utilizing low boiling point ethanol. Inside a centrifugal decanter, ethanol dissolves the sulfide-based solid electrolytes, while spent cathodes drop out as a solid precipitate. By utilizing vapor pressure dynamics rather than smelting furnaces or acid leaching, engineers can isolate the specific components needed without reducing them back to raw chemical feedstocks. To quantify the thermodynamic cost of these recycled materials, the immense blue materials input bar for hydrometallurgy dwarfs the direct method. That upstream acid production translates directly into severe greenhouse gas emissions, shown here, whereas direct solid electrolyte recovery emissions stay remarkably low. Direct recycling of solid-state batteries reduces greenhouse gas emissions by roughly 80% compared to conventional methods. It provides a thermodynamically viable path to scale these architectures globally. The final engineering question is whether a directly recycled solid-state electrolyte actually performs to the same standards as a pristine one. After the ethanol is recovered, the sulfide solid electrolyte is thermally annealed under a vacuum. This direct regeneration step restores its pure phase and local chemical structure. This electrochemical impedance spectroscopy chart provides the empirical proof of that recovery. Looking at the Nyquist plots, the recycled blue curve tracks precisely with the pristine black curve, showing minimal deviation. The recycled solid electrolyte returns an ionic conductivity of 1.48 millisiemens per centimeter. It operates in the exact same order of magnitude as the 1.62 millisiemens measured in the pristine material. We do not have to sacrifice energy density or conductivity metrics to achieve closed-loop material sustainability. The solid-state storage roadmap relies on two parallel engineering tracks: the 20C interface stability, demonstrated by the Chinese Academy of Sciences, and the thermodynamic life cycle framework modeled by UC San Diego. Displacing lithium iron phosphate by 2035 depends on a dual-front engineering victory. Success requires stabilizing the lithium fluoride interface to allow for 3-minute charging. Simultaneously, these cells, whether polymer, sulfide, or oxide, must be designed to be unpacked through low-heat solvent separation. In solid-state manufacturing, engineering for end-of-life recovery is synonymous with engineering for production scale.